Now we're getting into Beer's law. And Beer's law comes into place after you have really identified the unknown compound by ratcheting your slit down to the peak wavelengths and securing the peaks within that peak wavelength and the look of that graph, comparing that to knowns of compounds. So there are literally books of knowns and absorption graphs that match that. So you can look up in the index 539.5 nanometers and come up with a set of compounds that match that, and then go to your particular absorption spectrum, and see if those match for the unknowns. And that's one of the ways you can identify an unknown, is by matching your absorption spectrum in a very narrow wavelength on the peak to a known absorption spectrum on that same wavelength. The reason you use the absorption peak as your wavelength to pinpoint and get a little tighter to is because that absorption peak is showing you that the compound is exquisitely sensitive to that wavelength. And so if it's exquisitely sensitive to that wavelength, you can tell little pros and cons on either side of the wavelength where the absorption might drop off. And you can really pinpoint that when you have sensitivity in that wavelength area. So first step is to find the unknown. Start with a broad slit, move down along the peak, and compare it to your knowns. Second step is to look at the concentration of your compound in your sample. Two very different things, and Beer's law can help us with the second thing. Beer's law says that you can determine the concentration of a compound based within a specific range of concentration, because the range of concentration is directly proportional to the absorbance at that peak wavelength. So the greater the concentration of solute compounds, the greater the absorbance at the peak wavelength. Now, an advantage of Beer's law is that we can go through another book that tells us all of the absorbances along different concentrations of compounds at their peak wavelength. So there are books literally that will tell you about peak wavelengths and identifying unknowns. And there are books that will tell you the absorbance along a line for the peak wavelength of your known compound. And Beer's law helps us with that. So the first step, of course, is to identify your unknown by matching your absorption spectrum to the known absorption spectrums. The second step is to graph the known concentrations of that compound along Beer's law. So let's look at what that looks like. That would look something like this. This is a compound here. Let me move myself up here so you can see a little bit better. This is a known compound. And this is the absorbance along the y-axis of different concentrations of that known compound. And in fact, you see here that at low concentrations of this known compound, this, what are we calling it? Chemical A, the Beer's plot of chemical A. At low concentrations of the known compound, you will have low absorbance. And at high concentrations of this known compound, you will have higher absorbance. What you do is, after you have this Beer's plot developed on your graph, you look at your own absorbance on your own absorption spectra and match it for the peak wavelength, so that at your peak wavelength, you might have had an absorbance of 0.4 at 560 nanometers. So you come through, my absorbance is 0.4. Where does it hit the line and intersect with it? Here, you go straight down and you can pinpoint a concentration in millimoles for that compound in your specific sample. So that is your way of looking at your peak absorbance at your peak absorbance wavelength and comparing that to find out not only your unknown, but the concentration of your unknown in your sample. When we look at your procedures for this lab, you will be doing this on a lab that is online for a simulation. It's a very nice simulation for activities 1 and 2. And when you go here, please watch the video. It will help you. It's a very fast video. I suggest you ratchet down the speed of the audio. I tell you how to do that in number 2 here. And what it will do, it will help you to move your distilled water and your reagent, your methyl orange, and your beakers into your workbench, and then to apply your spectrophotometer to that. In this lab, unfortunately, you're not doing a blank first. I wish you were. This lab gives you the spectrum for methyl orange, and then you work from there. I wish you were doing the technique so you would work with the blank and then work with the methyl orange solution. But when you see this through the spectrophotometer that's listed here, you will be downloading the absorbance table for methyl orange, not methyl orange plus water, just methyl orange. It's a good lab. I just wish you had that step. You are going to now create a line graph in Excel from your data from the absorption spectra. You learned how to do this in your scientific writing lab. Now you're going to employ it. You're going to use proper CSV format to do that. When you have that graph, you're going to look for the absorption peaks of methyl orange. You're going to write down the absorption peaks. You're going to make sure you have units. And you're going to do some analysis in here. What colors does methyl orange absorb the best? What wavelengths does methyl orange absorb the least? What colors does methyl orange absorb the least? Then you're going to do some analysis on why that is so and what blank you would use for this experiment. When you go and do your second procedure, you will be using the same website for the second procedure. You will be using a different reagent. In this case, you would be using bromocresol green instead of methyl orange. You will use the same things, the distilled water, the beakers, and you will be using them in the same measure. You will be doing the same absorption spectra down here. Sorry about that. My left hand is not nearly as facile as my right hand. It is really hard to back that up, but I'll get that right. I'll get it right for you. And you will be doing the same graphing and answering analytical questions as well for this. Please use complete sentences when you do your analytical question and answers. It really makes you look more professional. And for your third activity, you're going to be preparing a Beer's law plot. You're going to be going to the Colorado EDU sims. They're great sims. I use them a lot for my meteorology and astronomy classes as well. You're going to be following these directions here to look at the compound, which is now known, of cobalt chloride, and you are going to be seeing the concentration of cobalt chloride in your specimen that you have. You are going to change the concentrations of your specimens as though you're doing 5 or 6 different runs with different concentrations, and you are going to be looking at the concentrations and the absorption in here as well, so that you will be putting this together, putting that in, and following this information out. I hope this helps you out, and I'll see you on the other side. Take care.